Welcome to video 7 of lecture 2. Today we will talk about continuous random variables. The previous lessons concerned discrete random variables and their probability distributions. In this lesson we will talk about continuous random variables. So in this case the probability mass function concept does not apply, so we will introduce the concept of probability density function, which is the most similar concept to probability mass function for the case of continuous random variables. We will also talk about the implications of having a cumulative distribution function for continuous variables, and finalize by talking about how we can calculate the expected value, the variance and the standard deviation of continuous random variables. The range of a continuous random variable is in the form of an interval or a union of intervals, and that's what distinguishes it from discrete random variables. Because between any two consecutive numbers in the range, you have an infinite number of other numbers. So the probability that the random variable assumes one of the numbers in the set is actually equal to 0. So we have to find alternative ways to deal with this kind of variables. So to simplify, consider these rules. Whenever we talk about probability mass functions, in the case of discrete random variables, we will now be using probability density functions for the case of continuous random variables. And whenever we use sums, we will now use integrals. Those are two basic rules that try to help memorize how we can deal with continuous variables instead of discrete ones. So consider three examples of continuous random variables. First, the exact average number of family members of a Dutch family selected at random. The average number of defective light bulbs done in several inspections. The exact lifetime of an aircraft engine blade. All of these examples are examples in which the range is not just restricted to a set of discrete items, but it's an interval of numbers from the set of real numbers. So let's figure out, before we introduce probability density functioning, why the probability that the random variable assumes a given number equals to 0 for continuous variables. When we deal with continuous random variables, we are interested more in intervals than in points, than in given points of the interval. So for instance, when we say, what's the probability of your friend arriving at 1:32? What we actually mean is, what's the probability of your friend arriving between 1:31 and 1:32? This probability is non-zero, as we are referring to an interval of time that has more than the length of 0. The cumulative distribution function of a continuous random variable is a continuous function. Remember that the jumps in the cumulative distribution function of discrete random variables meant that the jumps corresponded to points where the probability were different than 0. The fact that the cumulative distribution function does not show any jumps, that it's continuous for continuous random variables, is consistent with the intuition that the probability of a given that the random variable assumes a given value equals to 0. So we can also say that a random variable is continuous if the cumulative distribution function is continuous. Since we have this fact that we cannot calculate the probability of a random variable being a certain value in the range, we have to define an alternative way of describing the probability distribution instead of the probability mass function. So in this case, we typically use the probability density function, and the probability density function has to do with limits. In fact, it's the limit of the probability of the random variable being in a very, very small interval around the point of interest over the total length of the interval. Because we know this useful formula, we can apply it, and we get the derivative of the cumulative distribution function. So whenever we want to estimate the probability density function at a certain number, we just calculate the derivative of the cumulative distribution function. Pretty easy, right? So useful properties to know. The probability density function is always greater or equal than 0, because it's always associated with probabilities, right? If you integrate the probability density function over the entire real line, you get 1. And the probability of the random variable being in a certain interval, including in a certain interval of a to b, excluding a and including b, equals to the cumulative distribution at point B minus the cumulative distribution function at point A, which is basically just to integrate the probability density function between A and B altogether. There are a number of interesting distributions, continuous distributions that are worth knowing, and we will discuss them in the following lessons. To estimate the expected value of a continuous random variable, you use kind of the same logic that you would use for discrete random variables, but instead of adding the partials, you integrate. So the expected value of a continuous random variable is the center of gravity of the probability density function. You calculate the variance and the standard deviation in the similar way as for discrete random variables. And these are the learning objectives for today. It's very important to know that we should not calculate, that it's not possible to calculate the probability mass function in the case of continuous random variables. And for that reason, we need the probability density function. And this all has to originate, all this problem originated because we cannot calculate the probability of the random variable assuming a certain value. So thank you for your attention and see you next lesson.